The basic rules of probability are pretty straightforward. We have favorable events divided by total events, but counting those events is the tricky part. And so there's lots of things that we have to work with in doing so. Just looking back a little bit on the basic probability that we did, and then we'll jump back into the multi-stage stuff from section 2. So big ideas from the basics is there are two branches of probability. There's theoretical and experimental. And theoretical sort of exists, but in a way not really. But either way, it's favorable over all outcomes. And so we just have to find out clever ways to figure out how many favorable ways are there something can happen and how many total ways are there something can happen. One of the rules, the only rule we have so far related to, besides the division there, is when we look at two things happening. So the probability of some event A happening or some event B in the same situation. Under some circumstances, it's just the probability of A happening plus the probability of B happening. Like probability of having a male child or a female child, right? Well, so we'll have 1/2 chance the child's male, let's say, and a 1/2 female. That's not quite right, but it's close. And that gives us all the possibilities. But sometimes there's some overlap, and we have to remember that occasionally we have to subtract that overlap. And that related to the Venn diagram work we did quite a while back when we played with sets. And so sometimes analyzing probabilities, trying to find out what's going on, pictures like a Venn diagram can be helpful. So if this is A and this is B, then A or B happening is everything involving A or B together. And the overlap gets counted in multiple spots. It gets counted in A and B, this region right here. And so that is that part right there. So that takes out any double counting that's possible. So that was one of the ideas we looked at 2 classes ago, along with the basics there. And then we moved on to multi-stage probabilities. And that's where we look at more than one thing happening in sequence or together. And then tree diagrams became important, or tables. And then there's one big idea I still want to look at with respect to multi-stage probabilities that I haven't talked about yet, but hopefully you read about it, and it's the idea of independence of events. And I got a couple of cases we can look at the idea of independence. So before we do that, we're just going to play with another tree diagram situation. I'm just going to bring up an example. So I am in a family of 3 children. I'm the oldest. So we have Gary, just less than a year younger than me is my brother Keith, and just less than a year younger than Keith is Tracy. So there's 3 of us here. And Tracy is a girl, by the way. So we have male, child, male child, female child. So in this family right here, there are 2 boys out of 3 total. Oops. So what I'm wondering is, what is the probability of having 2 boys out of 3 children? We could kind of generalize this and look for even more information. So if we wanted to look at the number of boys and the probabilities related to that for 3 kids total, I had a friend who there were 3 boys in the family, so there could be 3. My family had 2 boys. It's possible there's only 1 out of 3, but there's also possible there's no. So if we're just looking at boys versus girls, you could have 3 boys, 2 boys, 1 boy, or none out of the 3. And the same could be said about girls. So I want to fill out this table eventually. And I want to answer this question first. Now, I have a good amount of information, but I have to make some assumptions about this to continue. And one of the assumptions is about the probability of having 1 boy out of 1 child. So we have to answer that question first. Probability 1 boy, 1 child family. And so the usual assumption is that we're just as likely to have a boy child as a girl child, so we say it's 1/2. Genetically speaking, that's not quite true. Genetically, boys are more likely to be born than girls. However, if you look at any age population in general, you're going to find there's more girls than boys, and that's a whole nother story. But we're just going to go with the reasonably simplified fact of there's a 1 in 2 chance of having a boy child, right? So as a decimal, we could call that 0.5, 5/10, or we could write it as a percentage, 50%. Now, the probability of not a boy would be a girl. So we're going to assume that either a child is a boy or a girl. So the probability of not a boy, and again, we're just considering 1 child. That's going to be the same as the probability of having a girl. And that's also going to be 1/2. So we just have 2 things. So it's like flipping a coin. It's either a boy or it's a girl. It's either a head or a tail. I'm not equating heads with boys and tails with girls, by the way. Anyway, so now we're going to build a tree to see what happens. So children definitely come in order. 1 comes out first, then another and another. Even if there's twins, there's a first and a second. So we're going to have a first child when we make our tree. We're going to have a second child when we make our tree, and we're going to have a third child when we make our tree here. And so for the first child, either that child is male or female. Sorry, I'm switching between boy and girl, male and female, but hopefully we all got that straight. Now, another thing I have to assume is that it doesn't matter, kind of like flipping a coin. If you get a head and then you flip again, it doesn't matter that first one was a head. So we're going to assume this idea of independence, that if your first child is a boy, it doesn't affect the chance of having a second boy or girl child. So that's another assumption I'm going to make here. I'm going to write that up top. Assume independence. Meaning having a male child, for example, does not affect the gender of the second child or the next child. And it turns out statistically that's not quite true, but it's close enough for most cases. So then for the second child, if you had a male child first, you could have a male or you could have a female child in the next round. Same thing down here. If you had a female first, your next child could be male, your next child could be female. The other day I introduced the idea of putting numbers on this. So the probability of a male child is 0.5, probability of a female is 0.5. And that continues along the tree. Those probabilities don't change if we have this idea of independence, which we'll look more at in a little bit. And then we go again. So third child could either be a male or a female from that first line. In the second line here, could be a male or a female. It's getting tight here. Down here, could have a male or a female, just gonna have enough room. And down here could be a male or a female. And then think about our rule for counting we talked about. There are 2 choices for the first child, 2 choices for the second, 2 choices for the third. So as far as our denominator here, we have 2 times 2 times 2, which gives us 8 total possibilities. And from the branching of this tree, we can see we double each time. So 2 doubled is 4, doubled is 8. So there's 8 possibilities up here. So next I'm just going to list what those are out here. They are, along the reading through the first one, male, 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 and then male, male, female. So the tree gives us a nice way to keep track of things and not lose track. Male, female, male, male, female, female, and that's my top 4. Going to the next branch, male, male, sorry, female, male, male, female, male, female, 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 male, and at the bottom, finally, female, female, female. Always a good idea just to make sure, again, I always went male, female, male, female, male, female. If you bounce around, it's not a big deal, but you just have to keep track. Did you follow the right branch when you're listing the results for each of these? And a lot of times I'll always kind of double check. Did this really relate to the line of the tree? I thought it did. I should finish the last set of probabilities there. Each of these is assumed to be 50% chance. So that they're each 50% chance at any particular point means that's the idea of equally likely probabilities that we talked about before. If each stage was equally likely probabilities, at the end, each of these should be equally likely, so that, for example, male, male, male is just as likely as male, female, female. So each of these should have a 1/8 probability because there's 8 of them and I started off with that equally likely assumption. Other way to check that is if you follow any particular branch, like let's say this one right here, the male, female, male, and we multiply the probabilities along the way. So I'm on this branch right here. I had a 0.5 probability followed by a 0.5 probability followed by a 0.5 probability. And if we double check that on a calculator, it should come out to 1/8. So calculator would be handy today. I'm going to use Desmos. Scientific is a nice one. It's like a handheld scientific calculator. So 1/8 was the first probability I assumed, hoping they were equally likely. As a decimal, that's 0.125. And then I took 0.5 and multiplied it by itself 3 times. And notice that comes out to the same decimal value. So either each of these come out to 125 thousandths, 12.5%, or 1/8. So we have a bunch of ways to name them, but they all came out to be the same thing. Now, this tree now allows me to fill out my table. When I do something like, say, what's the probability of having 3 boys or 2 boys or 1 boy or none out of 3, I need more information. I need the assumptions about each possibility, male, female. I need to know about independence. I need to know if probabilities are equally likely. And the tree is nice too to make sure we're getting things right, because I can't assume that we're just as likely to have 3 boys as 2 boys. And if you look at the tree here, 3 boys only happened once, right? Male, male, male. It's the only time that happened. So there's a 1/8 chance this happened right there. If we focus on 2, I'll use red for 2 here. 2 boys happened here. 2 boys happened here, right? 2 males here. And that's the only other time I see it. So it looks like that one right there is 3/8. Looking for 1 male. Welcome, Julian. 1 male happened in this 4th line here, 1 male. So I'm counting how many times I saw 1 boy. It happened here, and that one, and then down there, it happened again. So that one looks like 3/8. And then finally, none, that would be all girls, all females. So there is one way that can happen, it looks like. Whenever I set up a counting system that accounts for every possibility, and having 3 children, you can either have 3 boys, 2 boys, no 1 boy, or none. Those are all the possibilities. If there's no intersection between having 3 boys and 2 boys, exactly 3 or exactly 2, that is. If I add those probabilities up here, what should these add up to? Anyone?
Should add
8
up.
over 8.
8 over 8 or 1, yeah. So anytime you look at all possible probabilities and you have no overlap between them, they should always add up to 100%. So in this case, 8 over 8, 100%.
Okay, I might have a silly question.
So,
So how does this change in probability when you switch the question is what is the probability of having a boy first and then a girl and then a boy, and
Yeah, so-
not just having
yeah,
two boys?
So that's a different question, right? So the probability I asked was, what's the probability of having 3 boys out of 3 children? We could ask a different question based on the tree we have here. So I'm just going to go to a new page. We'll come back. I could ask, what's the probability of having 2 boys out of 3 children? And that is not a simple event because there's more than one way that could happen. So that would be the probability of having a male child, and then a female, or having a male child, a female child, and then a male child, or having a female child, a male child, and then another male child. Those are the only 3 ways you can have 2 boys. Either the female was born last, the female was born in the middle, or the female was born first. Now, these are simple events and there is no overlap between these 3. So it turns out that's the same as probability of male, male, female, plus probability of male, female, male, plus the probability of female, male, male. These are each simple events here. Simple events in having 3 children means there's a 1 out of 8 chance for each of them happen. So that's 1/8 plus 1/8 plus 1/8. Alternatively, right, I can look at the list of things that happen and we could see there were 3 ways that could happen. So I can kind of just looking at the 3 8s without going through all this crazy notation there. And then your question was, well, what about the probability of having a female first? I can't remember the order you said, but it was a specific order, right? A female, then a male, then a male. Or maybe it was the female in the middle. There's only one way that can happen based on the data that I drew out in my tree here, right? This one, where did it go? This one right here. There's only one way female happens first and then 2 males out of all 8 possibilities. So that one is definitely just 1/8. And it is really important not to take things for granted in a situation like this. So again, when I staged 2 questions at first, and I did it that way on purpose. One was, what's the probability of having 3 boys out of 3 children? And then I started looking at, well, what about 2 boys or 0 boys or no boys? And at first glance at that second question, number of boys versus the probability, you can either out of 3 kids have 3, 2, 1, or 0. One might look at that and say, well, there's 4 different possibilities. They must be 1/4 each. But we got to be really careful about never making that assumption just up front. And we actually have to dig a little deeper to figure out, is that really true? And when I thought about my assumptions, like, hey, what is the probability of having a single boy, only 1 child? 1/2, 1/2. This assumption about independence was important, going from one set of branches to the next. Once we thought it out a little farther, we could see, well, there's a lot more possibilities than 4. Turns out there's 8 different ways 3 children can be born in terms of gender. And then we get this distribution in terms of counting boys that isn't equally likely for each case, right? There's a 12.5% chance of having 3 boys. And then what would 3/8 be? 37.5, is that right? Around a 37.5% chance of having exactly 2 out of 3 children be boys. So every situation is different. The basic idea of probability is pretty easy, right? Favorable over total, but figuring out a way to carefully count what's going on, that's the hard part. And we have to find a system where we're sure we kept track of everything, we have our assumptions clear, so we can come up with some reasonable answers there. Other questions on this? That was a good question. So I'm not going to draw this out, but just going to throw it out there. I have a few friends that have 6 or 7 kids each, and the tree for them would be a lot bigger, right? Imagine 6 kids. So just a brief note on that. What about 6 children? And just think about the total number of ways 6 children can be born in terms of gender. So again, we're not going to draw the whole tree. It's a little tedious. But how many possible outcomes are there? Well, again, we have a first child, a second, a third, a fourth, a fifth, and a sixth. And either child could be male or female. So as far as choices go versus number of children, there's always 2 choices for each child. So the gender distribution as in terms of when each gender was born would be 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. I think I got that right. There are 64 possible ways to look at the gender distribution in order of birth for a 6-child family. Okay. Now 64 is not a big number in the grand scheme of things, but it just, again, think about a tree branching out 6 times like this one, and then you'd have 64 end results at the end, alternating between all males and all females, top and bottom, and then mixed up with males and females in the beginning. It's doable. Once you do like 2 children, 3 children, 4 children, you kind of see a pattern to it, and there's easier ways to come up with it. But the bottom line in our working with probabilities right now, the tree is kind of our most powerful tool, and most questions are answerable that way if you're careful and you have the time. All right, so I need to pay more attention to this idea of independence that I just introduced in that example. Either independence of events. So what that means is one event result has no effect on future events. And with the children, that is a dangerous assumption, and it's not completely true, but it's close enough. It turns out having a male child, it's slightly more likely the next child would be male, but it's more like, you know, a 52% chance instead of a 50% chance of having a male. So it's not huge, but there's a little effect. Flipping a coin, for example, what's the probability of getting a head on a second flip, knowing there was a head on the first flip? So does the knowledge of seeing the coin flip and knowing it was a head affect what happens when you flip it again? So any coin I flip was probably flipped in the past. Did that past of the coin have any effect on what happens when I do it presently? Right? So this is what's called a conditional probability. And there's a technical definition for how to deal with that. We're not going to worry about it because we only have this short time to work on probability. If we spent a few weeks or a whole quarter on this, then we'd break it out more carefully. But what's your gut opinion on this? Does a first flip of a coin affect the second flip of a coin?
No.
No, it doesn't. The coin flips, it's a head or tail. We believe it's pretty random and that the first flip doesn't matter. So this probability right here is exactly the same as the probability of just getting ahead on the second flip. Right, so this knowledge doesn't change anything. So that's the idea of independence. Does past knowledge change a future probability? If it doesn't change it, you're good. Okay? That's that. There's a rule related to it that the probability of A and B happening is equal to the probability of A happening times the probability of B happening. So this would be like getting probability of head on the first flip and getting ahead on the second. If independence is true, then that should be the same as getting a probability of a head second times the probability of getting ahead first. The probability of getting ahead first is 1/2. The probability of getting ahead second is 1/2. So then if they are independent, then this should be a probability of 1/4. And we played with this idea the other day in class. So that's a place where we have independence. Now we don't always have independence. And before I do this, I just want to make sure everybody is familiar with a deck of cards. Let's see, this one maybe. All right, blow this up a little bit. All right, so a standard deck of playing cards look like this. There is one marker on an ace, so ace is like a 1, and then 2 has 2 marks, 3 has 3 marks, moving on down to 10. So we have these cards, we can call them 1 through 10 or ace through 10, and then we have the royalty, the jack, the queen, and the king. So we have 1 through 10 plus jack, queen, king, so there's 13. These are clubs, these are diamonds, these are hearts, these are spades. I'm bringing this up right now just because I've had classes before where people were not familiar with a deck of playing cards. I just want to make sure everybody is familiar with this. So again, points of familiarity, that's a tough one, there are 13 cards. Forget about jokers if you know about those. We have 2 colors, black and red. The black is either a club or a spade, and the red is either a diamond or a heart. So this is the deck of cards here. So I want to look at some probabilities related to decks of cards. These get hard fast, right? Our denominator for just one draw from a deck of cards is 13 times 4, or 52 cards. So it's not like rolling a dice, 6 choices for the first roll, or flipping a coin, 2 choices. We have 52 choices on the first shot. What if we do 2 cards? Okay, so independence with a deck of cards. I guess I should bring that picture in here. Shrink it back down. Come on, shrink please. Go. It's always nice to look at when you're thinking about card probabilities. And I'm not going to teach you how to play cards or gamble. My belief is that I know too much math to gamble. Ooh, that came in weird. What's up with that box there? Don't know. Oh, I accidentally zoomed here. All right, can I fix that? All right. Oh, down here maybe? Oh, and then I messed up my thing. Let's try it again. Nope, not that. Sorry, technical difficulties. Let's just start over. Okay, so here's my deck of cards here. What I want to look at is just drawing cards out of a deck. So the probability of drawing a king. So if we look at the deck here, we can see there are 1, 2, 3, 4 kings. So there's 4 favorable outcomes out of 52. So it'd be 4 over 52. Oops. And that could be reduced if we wanted to. I'm just going to leave it 4 over 52. That's the probability of drawing a king. Next thing I might ask is, what's the probability of drawing 2 kings? Now this question's a little bit trickier because there's 2 different ways this can happen. So I shuffle the deck of cards and I draw a card and I look to see if it's a king or not. I put the card back in, reshuffle, draw again, right? So that's drawing with replacement. Or we could do like it's normally done when you're dealing cards in a card game is you once a card is out, it's out, it doesn't go back in. Okay. So let's assume here we're drawing without replacement. So we pull a card, we keep it. So let's just think about, we know what's happening for the first one, right? It's 4 out of 52. So let's suppose on the first drawing, I got a king. So either when I make this drawing, one of 2 things is going to happen. Either I get a king when I do my first draw, or no king, right? And there's lots of ways I can get no king. So let's suppose I did draw that king, right? I got a king in my hand, and I'm about to get my second card right after that, right? So I pull one card, I'm pulling another card from the deck. Now, right now, we know that there was a 4 out of 52 chance of getting that king, and I'm about to draw another king. Now, how many kings are left in the deck?
3.
3 kings left in the deck. How many cards are left in the deck? 51, nice. So the probability of drawing 2 kings would be, I got a king the first time, 4 out of 52. I got a king the second time, so this is the 3 out of 51 is my second king. So altogether, when we move through a tree like this, the probabilities get multiplied. So that's 4 out of 52 times 3 out of 51. So did the probability of drawing a king the second time change from the first time? The answer is yes, it did. So the important thing to note here is if you're not putting the cards back in the deck, then the drawings are not independent. Whether I drew the king or not affects the next probability. So I did get a king, change the probability there. So that's the idea of independence. So sometimes situations are independent, like flipping a coin, rolling a die. Sometimes it's not clear, like having a child. And for having a child, we just have to look at lots and lots of data to see. Okay, look at all the births that happened lately. How many times did someone have a male child and then a male child after versus a female child after? And my recollection is the data indicates that you're slightly more likely having a male child first to have another male child. Right? So it's like instead of a 50% chance of having a male on your second child, knowing you had a male on the first, it's like maybe 51 or 52%. Goes up just a tiny little bit. So this is the idea, again, of independence. Does something happening affect the next thing? And sometimes it does. If I wasn't replacing the deck, if I was replacing them back in the deck, like I drew the card, I put it back in, I shuffled it, I draw again, then it would be 4 to 52 times 4 to 52. But this time it changed. So this is just drawing 2 kings. I'm not even looking at this other branch because my question asked, what's the probability of getting 2 kings? Okay, so down here is not getting a king, which means it doesn't answer my question. So that part of the branch is irrelevant. Kind of like if we look back, so I didn't finish the tree on purpose. If I look back here, okay, looking back here, what's the probability of getting 3 males? Well, that only happens on this branch right here. Any other branch where there's a female, it's not even worth looking at those branches. So this is the only branch that mattered when I was looking at just having 3 children. Now, if I wanted to answer other questions, like what's the probability of getting 1 king, then I have more work to do. Okay. So I'm just gonna keep going then with this just for fun. So when I draw thinking about kings, either I get a king or I don't get a king. Now in this top line here, it is possible my second drawing was not a king. So let's continue this branch up here. I'm gonna pick a new color to continue. All right, so I know I have a king. That's the branch I'm on. This top green one was getting another king. This bottom one is gonna be not getting a king. So consistent, no king on this branch. Okay, so how many not kings are there? Well, there's 52 cards. There's 4 kings total, so there must be 48, am I getting that right? Cards that are not kings. Sounds right. So there's 48 possible cards, knowing there's already a king out, right? So all the other not kings are still there. I have 48. How many cards are in the deck at this point on my second drawing? I'll look back at Jimmy's answer from before, 51. So the probability of getting a king and then not a king is, for this branch, 4 out of 52, we got a king, times 48 out of 51, I didn't get a king. Let's go down to this branch that we didn't do work on before. So this is the first drawing from the deck. Nothing's come out of the deck. There are still 52 cards in the deck. How many not kings are there? There are 48 not kings. So the first drawing, that's not a king. There's a 48 out of 52 chance of not getting a king. Then we move along. From there, either we get a king or we get no king. So those are the 2 options. In this branch of reality, we don't have a king. So how many kings are in the deck on this branch right here? Let's say I have an ace in my hand. How many kings are still in the deck?
4.
4, thank you. Yeah, there are 4 kings in the deck currently. 1 king is missing, so that's 4 out of 51, the probability of getting a king on the second draw, knowing you didn't get a king on the first draw. All right, let's go down to the last branch here. So in this last branch of reality, we know we did not get a king. And now we know we're about to not get a king again. I already have an ace in my hand, let's say, for an example. How many not kings are left in the deck?
47.
47, right. And this is the second draw, so there are 51 cards. So in terms of thinking about a king, I can either, on 2 draws, I can either have 2 kings, no king, or 1, let's see, 2 kings, 1 king, or no king. We'll summarize that in a second. These are all the ways that can happen, 2 draws. So let's just fill this out some more. The third branch here has a first line of 48 out of 52 times 4 out of 51. The last one, no kings twice in a row, 48 out of 52 times 47 out of 51. And then if I just summarize these in terms of how many kings were present in these 2 draws. So number of kings. First line had 2 kings. Second line had a king followed by no king, so 1 king there. Third line had no king followed by a king, so 1 king there. And the last line had no king followed by no king. So if somebody asked, okay, you're gonna draw 2 cards, what's the probability of getting only 1 king? So I'm gonna try and answer that on the next page. So probability, only or exactly 1 king out of 2 cards. to answer that, I have to have some kind of tree or some kind of analysis that shows me the different possibilities. And the possibilities here, either I have a king and something else, so a king comma other could have happened, or I could have gotten some other card followed by a king. So those are the two possibilities. And we do have both of those written out over here in our tree. So that would be 4 out of 52 times 48 out of 51, king followed by no king. Plus, I look back at my tree, 48 out of 52, no king followed by a king, 4 out of 51. And notice those two fractions look pretty similar. 48 out of 52, 4 out of 51. They both have 4 times 48 in the numerator, and they both have 51 times 52 in the denominator. So I could summarize this a little bit by saying the answer is 2 times 4 times 48 over 52 times 51. And I just kind of want to look at that probability on a calculator just for fun, see it as a percentage for 2 cards. So calculator. So we've got 2 times 4 times 48 divided by 52 times 51. And the main thing of importance here is that the 52 and 51 are both in the denominator, which they are. And so I get a roughly 14.5% chance if we rounded to 0.1%. So that's about a 14.5% chance, approximately. Now, let's look at that idea of number of kings versus probabilities, kind of like the number of children in probabilities we looked at before. Number of kings, only 2 cards, versus the probabilities. So I can either have 2 kings, 1 king, or no kings. We just calculated the probability of getting only 1 king is about 14.5%. Let's calculate the other ones. 2 kings, if we look back, was, let's see, only one way that could happen. It's 4 out of 52 times 3 out of 51. So 4 over 52 times 3 over 51. And so there's less than a 1% chance. So if we round that, that would be like 0.5% roughly. So 0.5% chance of that. Pretty unlikely to get 2 kings out of 2 cards. And then no kings, that should be pretty darn likely. So that one was 48 out of 52, because there were 48 no kings. On the second draw, we lost a no king, so we have times 47, and there's only 51 cards. And that one ends up being 85.1. Now keep in mind, I'm doing some rounding here, and rounding multiple times in a row can cause accumulated error. So we're gonna end up with a slight error here in just a sec. So let's call that 85.1%. And these are the only possible things that can happen with 2 cards. Either you have 2 kings, or you only have 1 out of 2 kings in your hand, or you have no kings in your hand. Only 3 things can happen when you're thinking about kings and 2 cards. And if we add those up here, that we get a little bit of accumulated rounding error. If we went to 2 decimal places, maybe we wouldn't see it. But I'm going to get 0.5 plus 0.5 plus 1, carry the 1, and then, oh, it looks like we didn't get rounding error. Oh, good. 5, we get a 0, 8, 1, 10. We got, oh, no, we did get a slight, sorry, rounding error of 0.1%. If we didn't round and we just added those fractions together, it should be exactly 100%. So if to this one right here, I add the other guys, so to that answer, I add on the 4 out of 52 times 3 out of 51, and And add on to that, so let the computer deal with any possibly rounding. I had 2 times 4 times 48 over 52 times 51. I should get exactly 100% if I let the computer deal with the rounding. Okay, so we just got a little bit of rounding error. So that happens sometimes when we do approximate the fraction versions of it. But a couple things I'm trying to get at here. Independence of events means that one probability changes a future probability. One event changes the next event. And so that happened on every one here because the denominator changed because we didn't put a card back in the deck. So that's kind of the classic example of when non-independence happens. So these aren't independent events. The other thing here is thinking through a tree to kind of figure out what's going on. Now this was about as simple an example as I can get with 2 cards. If we try to throw other things in like 3 cards or 5 cards, you can imagine how much harder it's going to get. So we're not going to do any more with cards unless we had another week or 2 to play. But I do want to branch this into another example of independence. So another example this pops up in is choosing one small group from another. So a lot of examples of this come up. I used to coach middle school soccer, and typically the middle school girls, we kind of bunch them all together, and we might have 30 kids on the team. So there are 30 girls on a soccer team. And then from those girls, I have to choose a captain, or the team has to choose a captain. And then we also choose a backup, right? Like an assistant captain or backup. So the question is, well, how many ways are there to choose a captain and an assistant captain? So possibilities. For the captain, I think we're going to choose the captain first. There are 30 possible girls to choose from. Now, one of those girls is captain. She can't be assistant captain too, right? So when we choose the second captain, the chance of someone becoming the second captain is actually a little better because now there's less girls to choose from. So for the assistant captain, right, it's a little easier to choose. There's one less person in the denominator. So there'd be 30 times 29 possible ways to choose 2 people out of 30 for some team. And the team would be captain, assistant captain. Kind of curious what that number is. $870 different possibilities of who gets to be captain and assistant captain. 870. Wow. All right, let's see. Is that everything I wanted to go over about multi-stage probabilities? I believe that it is. So with that, there is one big topic I'm skipping in this section. We just don't have the time to do it. So be it. And it's not in the homework, and it's not going to be on the test, so we're not going to worry about it. Are there any homework questions people came across when they were doing the probability problems?